So we continue with the mathematics of artificial intelligence by looking at the math roadmap every artificial intelligence engineer needs. So in the first video, we had looked at 5 equations. Here we're looking at the math roadmap you need if you are intending to be an AI engineer. So basically, modern AI is built on 6 mathematical pillars, including algebra, linear algebra. In fact, we can put linear algebra and linear algebra together, but let's just split it like that. So algebra, linear algebra, calculus, probability, statistics, and optimization. So these are like the 6 pillars on which modern AI rests. These foundations lead directly to machine learning, deep learning, transformers, large language models. So if you remember what we talked about in the first video, or you want to check that if you had not seen it before now, you'll discover that the equations that drive all this are very simple equations, but we have them applied to large data sets, and then it makes so much difference. So, and the roadmap is like this. So understand algebra, then move on to linear algebra, where you talk about matrices and all of that. Then from there, you move to calculus, that talks about the rates of change. Then you go for probability. I mean, if you follow Keith Devlin's definition of mathematics as the science of patterns, so you see calculus is the pattern of change. Probability is the pattern of chances. Statistics, I don't know what to call that because we can still put probability and statistics together somewhat. Then you have optimization. That's about maximizing, making the most of every situation. Of course, statistics is all about making sense of data, right? Then machine learning is the next thing you go to there. So machine learning is like statistics in some kind of advanced at some advanced level, and then you go for deep learning. As the name implies, you do some. So deep learning is basically modeled after how the brain functions. I know all the thousands of neurons and everything we have in the brain. That's how what deep learning is patterned after. And then that takes us to the idea of transformers. In the I think it was in the second video or so, or was it the first video still, where I showed you a paper by Vaswani et al. I think in 2017. The book was never peer reviewed. It was uploaded on archive, and that was the introduction to transformers, where the idea of attention came up, and we saw the equation for attention, I think, in the first 2 videos or so. So that's the roadmap. So if you are intending to be an AI engineer, then you have to go through you have the mathematical foundation, and then you go to machine learning, then deep learning, and then you talk about transformers. So let's take these areas one after the other. So we start with algebra. By the way, I have all of this any of these topics you might be seeing here. I have a playlist on them on my channel. You just want to click on that and click on playlist, and you find all of them. So I mean, every none is spared. Algebra. Okay, well, yeah. I mean, it's by implication, right? I have videos dealing with algebra, then linear algebra in clear terms, then calculus, probability, statistics, and optimization. I have all this already done there. So in case you need to, you have no solid foundation in these areas, you can avail yourself the opportunity to look at the videos on this channel. So algebra and functions. A machine learning model is fundamentally a mathematical function. Basically, a machine learning model is fundamentally a mathematical function, and a function maps inputs to outputs. So you throw x in and you get y out of that. You make x obey a particular law and it results to y. So f of x implies y. Example, f of x equals x squared. So if you put x equals 3 as an input, then your output will be f of 3, which is 3 squared, and that is 9. So a machine learning example is something like this. Salary is a function of experience. So the model learns the function f from data. So whatever the function is, so the function takes up your experience and decides what your salary should be. That's as simple as that goes. So machine learning model is fundamentally a mathematical function. And then we go to the idea of variables and equations. An equation describes a relationship between variables, basically. So y is equal to 2x plus 3. So if x is equal to 5, then you have 2 times 5 plus 3. And that tells you that y is 13. So variables are the basic building blocks of every machine learning model. So variables, for instance, experience here, is a variable, and it determines salary, which is also a variable. So you can call experience the dependent variable, no, independent variable rather, and salary is the dependent variable because salary depends on experience. Then we go on to talk about exponents and logarithms. I have a playlist on indices and logarithms, so you want to check that. Of course, exponents is another name for indices. So exponential functions rather, appear everywhere in artificial intelligence. You see them everywhere. And then, for instance, you have f of x equals e raised power x. So when x is 0, you have e raised power 0, which is 1. When x is 1, you have e raised power 1, which is approximately 2.718. When x is 2, you have e raised power 2, which is approximately 7.389. And then you have logarithms as the inverse operation of indices. So if you have log of e raised power x, by the way, log is lateral log here. So except otherwise stated, maybe you have log base, then it will be indicated. But once you see log, you just take it like that for, I mean, in the arena of artificial intelligence. So the log of e raised power x is simply x. So because log is the inverse function of exponent. So you have important identities in log, which log a b is the same thing as log a plus log b. Log a raised power b is the same thing as b multiplied by log a. And logarithms are heavily used in cross entropy laws. I think we already saw that in the earlier videos where we try to minimize loss, and we use log, and because log helps to penalize log helps to ensure that the large values are brought within a reasonable limit. Then you have logs coming up in information theory, and one of the biggest key equations in information theory is the Shannon formula, that involves, it also involves log, right? Then you have probabilistic models too that also involve logarithm. So having taken care of algebra, so you see, algebra is all about variables, functions, and equations, and then we come to the arena of linear algebra. Now, linear algebra is the language of AI, basically. So linear algebra is the language of AI because everything in modern AI is represented as scalars, vectors, matrices, and tensors. So our neural networks are essentially large collections of matrix operations because you deal with large data, you deal with very heavy data from time to time. So like that. So let's talk about scalars, vectors, and matrices. So for instance, a scale 5, if you just have 5, it's a scalar. But you have a vector when you have this column vector 1, 2, 3, that's a vector. And you have a matrix if you have rows and columns. So this one has 2 rows and 3 columns. So row 1, 1, 2, row 2, 3, 4. Column 1, 1, 3, column 2, 2, 4. So this is a matrix now. The interpretation is that a scalar is a single value like 5, and um a vector is a list of values, well, either in a row. This one is in a column now, so it can either be in a column or a row. Then you have matrix, which is a table of values, like what you have in Microsoft Excel, SPSS, and every other spreadsheet style of thing like that. Then you have vectors now. So a vector represents a collection of features. Example, you have a person, everybody has a height, a weight, and an age, right? And these are very useful in calculating the health indices of a person, right? So so you can now make that into a vector. X equals 180, 75, and 30. So 180 for height, weight is 75, and age is 30. So in machine learning, every data point is usually represented as a vector. So if you pick the height, weight, and age of a person, that's one vector. But if you have another person, that's another height, weight, age. So you can now collect that for 10,000 people, 1 million people, and things like that. So in machine learning, every data point is usually represented as a vector. So in this case, a data point is a person and their information can be represented as a vector. Then we have simple things like vector addition. I have a playlist on vector too, so you want to check that out as much as possible. So vector, you have A to be 1 to B is 3, 4. So to add, you can add vectors of the same dimension. So A plus B here will just be 1 plus 3, 4, 2 plus 4, 6. So addition combines corresponding components, and that's why you can only add two vectors have the same dimension. Then we have dot product. We already saw the usefulness of dot product when we're talking about attention, the fifth equation that drives modern AI that we saw in the first video. So the dot product is one of the most important operations in AI, and the formula is this A dot B, which simply implies A1 multiplied by B1 plus A2 multiplied by B2 plus A. all the way down to an multiplied by bn. It's some kind of linear transformation, which refers to the first equation that drives modern AI that we saw in the first video, talking about talking about linear combinations, right? So if you have A to be 1, 2, 3, and B to be 4, 5, 6, or if you like, you want to write it as a vector like I 2j plus 3k and 4i plus 5j plus 6k. So the dot product will simply be multiplying component by component, as A dot B will now be 1 times 4 plus 2 times 5 plus 3 times 6. 1 times 4 is 4, 2 times 5 is 10, 3 times 6 is 18. If you add it up together, all together, you get to 32. So the dot product measures similarity and forms the basis of neurons. And along the line, you're going to see this idea about cosine similarity even in natural language processing. So that comes from this idea of dot product. So the dot product measures similarity and forms the basis of neurons. Then we go on to talk about matrix multiplication. Neural networks are mostly repeated matrix multiplications. For instance, you have A to be 1, 2, 3, 4, and B is 5, 6, 7, 8. The result AB is 19, 22, 43, 50. And how do we get that? We simply just multiply. I mean, I have a fast way of doing that, which I explained amply in the linear algebra playlist, and as well as the matrix playlist. That was the first playlist, by the way, on this channel, the matrix playlist. So you have something, you have A to be 1, 2, 3, 4, and B is 5, 6, 7, 8. What you just do, AB now is you have you want to multiply the two. So the first thing you do is because you have two rows here, you write 5, 7, 6, 8 twice. So 5, 6, 7, 8, then 5, 6, 7, 8. And the next thing you do is this row one, you put it over the first row, and row two, put it over the second row, 3, 4, 3, 4. And then you have 5 times, so here 5 times 1 is 5, plus 6 times 2, that's 12. Then 5 times 1 again is 5 times, okay, so, okay, no, something is not right here. This should be 5, 7, 5, 7, 5, 7, 5, 7, 5, 7, and then 6, 8, 6, 8, not like the 6, 8, 6, 8. So this 5, 7, right twice, 5, 7, 5, 7, 6, 8, 6, 8, right twice. Then 1, 2 comes over like that. So yeah, so 5 times 1 is 5, 7 plus 2 is 14. Then 6 times 1 is 6, 8 plus 2, I mean 8 times 2 is 16, right? So this is 7 times 2, 14. 5 times 3 is 15, 7 plus 4 is 28. 6 times 3 is 18, 8 plus 4 is 32. So if you put all of that together, you have AB to be 5 plus 4 is 19. 6 plus 16 is 22. 15 plus 50 plus 28 is 43. And 18 plus 32 is 50. So 19, 22, 43, 50. That's how it came about. 19, so 19, 22, 43, 50. So the first element you have here is this 5, 7 multiplied by 1, 2. So 1 times 5, that's what you have here. Then 2 times 7, you have that. So that's 5 plus 14, which is 19. So matrix multiplication allows information to be transformed between layers. So, I mean, what you see as matrix multiplication in the realm of AI, it is actually allowing information to be transformed between layers like that. And then we go on to talk about eigenvalues and eigenvectors, which hold a lot of meaning. We talked about it amply under differential equations and some other places, under matrices generally. So the definition is this, that you have AV equals lambda V, where A is the matrix, V is the eigenvector, and lambda is the eigenvalue. So that's the relationship between. So the product of a matrix and its eigenvector is equal to the eigenvalue multiplied by the vector. So the interpretation is that this matrix changes the magnitude of the vector, but not its direction. And it has applications in principal component analysis, dimensionality reduction, spectral clustering, and transformer analysis. So I've dealt with this in some other realms. I think, yeah, I know I've dealt with it under some kind of playlist also. So then we talk about calculus now. Calculus enables learning, because it is about change. So without calculus, there'll be no gradient, there'll be no backpropagation, which relies heavily on chain rule. So calculus helps us to do gradients, backpropagation, and without calculus, there'll be no deep learning too. So the central concept of calculus is the derivative. So that's differentiation, right? So talking about derivatives now, you're getting the rate of change of a function with respect of a variable with respect to another. So a derivative measures the rate of change. So if you are given f of x equals x squared, f prime of x, which is the first derivative of this function, will be 2x. Example, if x is equal to 3 now, f prime of 3, that's the second derivative of f of x evaluated at 3 will just be 2 times 3, 6. So the interpretation is that near x equals 3, a small increase in x produces roughly 6 times as much increase in y, basically. So, and that's the rate of change. So very close to x being equal to 3, a small increase in x produces roughly 6 times as much increase in y. So you can then use that to gauge if you are hoping for a kind of change, you can use this idea to do that. And then we go on to still talking about derivative, right? If f of x is x cubed, the derivative f prime of x is 3x squared. At x equals to, the calculation becomes f prime of 2, which is equal to 3 into 2 squared. That'll be 3 times 4, 12. So the slope at x equals to is simply 12. That means that near x equal to 2, the function, f of x itself is changes about 12 uh, produces is 12 times increase. It's increasing 12 times, right? I think I need to take out or maybe just even delete this because it's a repetition of the other one. Yeah, gone. All right. Then apart from that, we talk about derivatives, right? We also have partial derivatives. Now you talk about anything partial you hear in calculus is about dealing with more than one variable, more than one dependent variable. So we've been talking about f of x, that's f being a function of one thing, like salary being a function of only experience. But of course, in the real world, salaries is not just a function of experience, it's also a function of maybe level of education and all of that. So partial derivatives now, in machine learning, functions usually contain many variables. For example, you can have f of x comma y, which is x squared plus y squared. So now it's no longer just x, it's both x and y. Then partial derivative with respect to x. So if you are differentiating this now, you can differentiate partially with respect to x and partially with respect to y. So if you differentiate with respect to x, y is seen as a constant. So you get partial f partial x is 2x. Then partial derivative with respect to y, you get partial f partial, which is 2y. So each partial derivative measures sensitivity to one variable. Okay? Each partial derivative measures sensitivity to just one variable. And then we go on to talk about gradient. So in the case of gradient now, the gradient combines all partial derivatives. So definition, you have grad f to be partial f partial x partial f partial y. So for f of x comma y, x squared plus y squared. So the gradient is partial f, which is differentiate with respect to x, you get 2x, with respect to y, you get 2y. So the gradient points in the direction of greatest increase because it's like a kind of slope kind of thing. So the gradient points in the direction of the greatest increase. And that leads us to chain rule, still under probability. Now we came across the idea of chain rule for back propagation. So the chain rule powers back propagation. Imagine you have z equals f of y and y equals g of x. Then the z dx now, you see z depends on f and f depends on x. So to get how z depends on x now, you need to go through, it's more like you are linking up with a friend through a friend. That's what chain rule is like. So to connect z and x together, you have to pass through f, which is so to make z x's friend, it means that you have to go through f, uh who that is connect you have to go through y that is connected to x, like that. Then dz dx will be dz dy multiplied by dy dx. So deep neural networks repeatedly apply the chain rule through many layers. So that's basically what's happening. So in the case of neural networks now, you can then have maybe you can have like 1,000 functions, and then the chain rule will just continue like that. The connection just continues, many in many ways like that. And then we move on to another backbone another backbone of that an AI, another thing in the pathway of AI engineers when it comes to mathematics, and that is probability. So probability models uncertainty, all right, And machine learning really deals with certainty. Machine learning is just using data to think to do things. So instead, models estimate probabilities. So whatever machine learning is doing or AI is doing generally is just estimating probabilities. Like in the second video when I talked about ChatGPT being just a probability machine. So it's all about predicting with a level of probability that, oh, the next word that is to come is going to be this thing. So there's no certainty anywhere. It's just all about working with probabilities. So example, probability that a particular text you receive or a particular email you receive is a spam. If you say that 0.95, the meaning is that the model believes there's a 95% chance the email is spam. And that might be wrong, actually. It's all about making sure that it is right many times, many more times compared to being wrong, right? So, still under probability, we talk about the idea of random variables. A random variable represents uncertain outcomes. Example, rolling a die. And in rolling a die, possible outcomes include 1, 2, 3, 4, 5, 6. And the outcome, each outcome, either to get 1 or 2 or 3 or 4 or 5 or 6, has a probability of 1 over 6, like that. And then it takes us to the concept of conditional probability, which is very useful here, right? Because, in the ChatGPT video, I talked about the fact that the overall thing that is happening is we are checking what is the probability of the next token given all the tokens that we've had so far. What is the probability of the next thing that will be generated given that some other things had been generated, like the capital of France is. So based on that fact, what is the probability that the next word is Paris, given that the capital of France is at the first five words or so. So for conditional probability now, you're doing something like what is probability of A if we already have B in place? That's what that means. So that's probability of event A given event B. Then example, probability that somebody is going to have flu, given that they have fever, right? So probability of having flu, given that fever is observed. So if you have fever, it can be flu, it can be anything else. So but we want to be able to say that with a level of certainty, not perfect certainty, that you have so someone who has fever is actually actually has it because of flu. So, and closely related to the idea of conditional probability is the very important Bayes theorem. One of the most important equations in AI is the Bayes formula. That's probability that you get A, given that you already have B, is equal to probability that you have B given A multiplied by probability of A all over probability of B. And a worked example is here. So suppose that probability of having a disease is 0.01 and the probability that somebody tests positive, given that the person has the disease, is 0.95. That means that the person is correctly diagnosed. Then probability that someone is positive is 0.05. Then probability that someone has the disease, given that the person tests positive, is actually probability that the person has is positive, given that the person has the disease, that's 0.95. The probability of of having the disease is 0.01, and probability of having the disease is 0.05. And that's the answer. If you compute all that, you get 0.19, and that's like 19%. So it means that a positive test implies a 19% chance of the disease. So the fact that the disease somebody even tests positive does not guarantee that the disease is there, right? It only tells us that 19 out of 100 times the person actually has the disease when they are tested to have when they test positive. Now we go to talk about probability distributions. A probability distribution describes how values are generated, and we have some important distributions like Bernoulli distribution, normal distribution, binomial distribution, and uniform distribution. These distributions appear throughout machine learning. Interestingly, I have a playlist on on probability in general that also treats the distributions. So, talking about the normal distribution, which is about by far the most popular, the most important distribution in statistics is the normal distribution, and it follows the whole Gaussian. It follows the Gaussian. I mean, you can even call it the Gaussian distribution, right? So the notation is that X follows normal distribution with mean mu and variance sigma, right? Where mu is mean and sigma squared is variance. That's variance sigma squared, I mean. So the characteristics are that it is bell-shaped, it is symmetric, and it is common in natural data. So many things in life actually follow the normal distribution. Then, having talked about probability, we move to the fifth math thing that an AI engineer should be thinking about, which is statistics. So statistics extract information from data. Probability predicts future observations, and statistics analyzes observed data, right? So that's statistics. So you see, statistics and probability, they tend to be married together most times. Probability is about chances, right? But statistics extract uh, the information about all of that. So let's talk about the simplest thing, one of the simplest things to learn in statistics, which is you talk about measure. I have a playlist on statistics too, where we talk about measures of central tendency, measures of dispersion, and measures of shape, and all of that. So the mean, uh, by definition, is x bar, which is summation of all observed data divided by the number of observed data, something like that. An example is you have 246. So the mean is x bar, which is 2 plus 4 plus 6 plus 8, divided by not the number. So the sum of observed data plus their number. So the sum is 2 plus 4 plus 6 plus 8. The number is 1, 2, 3, 4. So, and that means that the mean of this data set is actually 5. Like that. That's mean. Then we have variance. These are two things we always talk about when in machine learning. So of course there are other things like mode and frequent mode, median, and all of that, right? But when you talk about distributions, you are especially normal distribution, you're talking about the mean and the variance. So variance measures spread. So it also talks about how spread apart is a particular situation. So by formula, right, the variance of x is actually equal to 1 over n summation of the deviation x minus mu. So the observed data minus the average, the difference between that squared. So so find the difference between each data and the mean, then square, sum them up, and divide whatever sum you get by n. That gives you your deviation. For instance, if for the same data we got before, 246, the mean, of course, we found to be 5 here. So it is that mean here that has been that x bar here is now what we call mu here. So for the variance, it will now be 2 minus 5 squared, 4 minus 5 squared, 6 minus 5 squared, 8 minus 5 squared. 2 minus 5 is 3 squared, that's 9. 4 minus 5 is 2 minus 5 is minus 3 squared, that's 9. 4 minus 5 is minus 1, square it, you get 1. 6 minus 5 is 1, square it, you get 1. 8 minus 5 is 3, square it, you get 9. So 9 plus 1 plus 1 plus 9 divided by 4. So you get 20 all over 4, which is 5. So the mean is 5 and the variance is also 5. That means that the data uh, on the average, the data are like 5 degrees spread apart, something like that. 5 spread apart. Of course, we also have standard deviation. Standard deviation is actually the square root of the variance of x. Example, if the variance of x is 25, then standard deviation is simply square root of 25, which is 5. So standard deviation is easier to interpret because it uses the original units. It uses the original units. Then we go on to talk about correlation, still under statistics. Correlation measures relationships. As you can see, correlation. How is this related to the other? So the range for that is -1 to 1. So correlation ranges from -1. It lies from -1 to 1. The interpretation is that R equals 1 talks about perfect positive relationship. So if I say that the correlation between A and B is 1, that means that A and B are perfectly related. So as A increases, B also increases, something like that. Then we have R equals 0, which talks about no relationship. So if I say the correlation between A and B is 0, that means that they have nothing in common at all. They have nothing in common. Then we have non-linear, no linear relationship. That's what R equals 0 means. Then R equals 1 means perfect negative relationship, meaning that if A and B have a correlation of -1, it means that as A is increasing, B is reducing, or as B is increasing, A is reducing, like that. So, and then we go on to the sixth thing, which talks about optimization, which I love so much because I like to get the best of every situation. So machine learning is optimization, basically. Machine learning is optimization because as you are getting more data, and as you get more data, you adjust the system. You improve the system from by getting more and more data, which is like a person getting better by getting more and more information. So the goal of optimization is to find parameters that minimize error. So the biggest thing we are doing in AI is to minimize the error of making mistakes, is to minimize the error of making wrong predictions, basically. So we want to make sure that we even though everything is based on probability, we are almost always correct. That's the big deal here. So we want to increase the loss function thing we talked about, which we are still going to see. So we find parameters that minimize error. So the quantity being minimized is called the loss function. So we talked about loss function before, and we have it here again. So a very simple regression example for loss function will be y minus y cap. Y is the actual value. Maybe you have a data set, a real data set you have, and y cap is the predicted one. So the square of that, that's for regression example now. So suppose that the actual data is 10 and you predict that it is 8, So the gap between 10 and 8 is 2. So when you square that, you have 4. So the loss function is 4. So this model seeks to reduce this value. So we want to make sure how can we do it so that we can make better predictions so that the loss function can be pretty small. So we want to do that. Then you also have gradient descent, which we had also talked about in the previous video. So the most important optimization algorithm is the gradient descent. I mean, I have a whole playlist talking about different kinds of algorithms. The playlist is under numerical optimization technique. So you have gradient descent, you have conjugate gradient, you have all kinds. But gradient descent is the most outstanding of them when it comes into when we come to talk about AI, machine learning, and all of that. You have gradient descent. So and it has an update rule. It's like under optimization, right? And you have to keep iterating until you get the desired result. And what determines the desired result is the level of error, the tolerance limit you have. So the most important optimization algorithm is the gradient descent, and it has an update rule that the new value of W, which is a parameter, minus is equal to the old value minus the learning rate multiplied by the gradient of the loss function, where W is parameter, like I said, and eta is the learning rate, and change in L is gradient. That's more like the derivative of gradient of the loss function with respect to the parameters on which it depends. So the gradient indicates the direction of steepest increase. So subtracting it moves towards a minimum. Because we are dealing with loss function, right? The goal is to make sure the loss function is as small as possible. That's why gradient descent works the best in this situation. So a practical example of gradient descent, right? F of x is x squared. So the derivative is f prime of x, which is 2x. So if you start with x equals 10 and you have a learning rate of 0.1, then your update value, the new x now, will be 10, the old x, minus the learning rate 0.1, multiplied by the derivative. The derivative at f prime of x, which is 2x, f prime of x equals 2x. Then f prime of 10 will just be 2 times 10, which is 20. So you have 10 minus 0.1 multiplied by 20, and that's 10 minus 2, which is 8. Then you can then go the next step. The next step now, so the new x would now be 8 automatically now becomes the old x, which is 8 now minus 0.1 times when x is 8, that means the derivative 2x is 2 times 8, 16. So you have 8 minus 1.6, and that's a 6.4. So repeated updates move x towards 0. So you keep going until you get to the desired level. So we've talked about all of that. So let's talk about machine learning mathematics now. So having talked about the fundamental maths things like algebra, linear algebra, probability statistics, calculus, and optimization. So we now want to talk about machine learning mathematics, which picks on ideas from some of these fields, some of these areas of mathematics. So we have machine learning combining linear algebra, since you have to talk about matrices or data points, data sets, and all of that. Then calculus, that's how the learning is happening, right? Or better still, yeah, the more data you get, things are changing. And you have probability, which is, everything we do in AI or machine learning is just about chance, it's just about probability. So we use all of this to learn patterns from data in machine learning, right? So we have the very first thing in machine learning is linear regression, straight to the point, simple. It's just the equation of a line, more or less, like y equals mx plus c. But here we say it is y equals wx plus b, where w is the slope and b is the intercept. So a very nice worked example now. Suppose that somebody has an experience of 5 years working on a job, and then the salary is modeled as 10 times experience plus the intercept 30. That means baseline. So this 30 is more like the baseline salary for anybody who comes in. So whatever the experience now is, it will be amplified by 10, and then we get the value. So the predicted salary in that case will just be salary equals 10 times 5 years experience plus the baseline salary. And it means that somebody who comes with a 5-year experience is going to earn 80, is going to earn 80, so to speak. The salary is going to be 80, whatever that 80 is, be thousands of dollars or pounds or whatever. So then talk about, we've talked about linear regression. Now we're talking about logistic regression. Logistic regression is basically used for classification. I talked about sigmoid function, which is represented here, and whatever happens at minus infinity, this function is actually zero. At infinity, the function is one. At 0, the function is half. So this function, the way it is, no matter what the values become, the function is always restricted between 0 and 1. So that's why it's used for classification. So the logistic regression uses the sigmoid function sigma of x, which is 1 over 1 plus e raised power minus x. And the probability is that sigma of x is always it ranges from 0 to 1. It doesn't go below 0 and it doesn't go above 1, whatever happens. So the output can be interpreted as a probability, in short, because probabilities are constrained from 0 to 1, right? They can't go below. Once you have a negative probability, something is wrong. And once you have a probability greater than 1, there's a problem right there. So, and then we've seen cross entropy before, right? Which talks about loss, cross entropy loss. Classification models commonly use L, which is minus y log p, minus 1 minus y log 1 minus p. So, example, if you have a true label where y is equal to 1, and then the prediction you have, which is p, is 0.9. So, the loss is going to be, so minus 1 log 0.9 minus, of course, 1 minus 1, that's 0. Of course, that automatically destroys that. So we have minus 1 log 0.9, which is simply minus log 0.9. And log 0.9 is going to be a negative value. So the minus multiplies it and you have 0.105. So better predictions produce smaller loss values. So our business here is to be sure that we have loss values as small as possible. That means that you want to predict accurately enough so that the loss function is also is low. Then we have, so I haven't talked about machine learning mathematics. Now let's talk about deep learning mathematics. So deep learning, like I said, has to do with how the brain behaves, all the wirings of the brain, the synapses, the neurons, and things like that. Deep learning extends machine learning by stacking many layers of neurons. So it's more like you have machine learning, but deep learning is not like you have many brain cells or something. Maybe machine learning can be seen as one cell, and then deep learning is like stacking so many of that together. So each layer learns increasingly complex patterns. So for instance, we have the artificial neuron. So a neuron, for machine learning, we had just wx plus b, but for deep learning, it becomes matrix. So z equals w transpose x plus b. Then applies so after that, we then apply an activation where a is now, this is now the output after activation. Z here is the output before activation. Then the activation happens here because you throw it into a function like this, into an activation function, sigma of z, and this is the fundamental unit of neural networks. So you see, it is just machine learning at an advanced level, like that. For instance, imagine you have a neuron calculation. You have x to be 2, 3, and the weights are 0.5, 0.8, and there's a bias of 1. What that simply means is that you have, so from what you have here, this is W transpose X. So you have 0.5 over 8, 0.508 in column form multiplied by 2, 3 in row form. And that's why you have 2 times 0.5, then 3 times 0.8 plus the bias, which is 1. So if you add all of that together, 2 times 0.5 is 1, 3 times 0.8 is 2.4, and then plus 1. So you have 1 plus 2.4, that's 3.4 plus 1, which is 4.4. So you then do the activation using a sigmoid function in this case. So A is equal to 1 over 1 plus e raised power minus 4.4. So it means the output after activation is 0.988, like that. So some kind of probability. And then having talked about neuron calculation now, we then come to the idea of neural networks. So you have the layer equation. So AL is F WL AL minus 1 plus BL, where W is equal to weights, B is biases, and F is activation function. So every modern neural network follows this structure now. So you have your layers here. So layers upon layers. So A, L, F, W. WA plus B. So this is still more or less like the same, uh, WX plus B here, but except now that you have more layers because you are dealing with neurons. So where W will be the weights, B are the biases, and F is the activation function here. So every modern neural network follows this structure. And then we've talked about backpropagation a lot of times. Training consists of four steps. First, you have the forward pass. Next, you compute the loss. Third, you have the back propagation. And four, you have update parameters. So back propagation repeatedly applies the chain rule to compute gradients. And then, having looked at machine learning mathematics and neural deep learning mathematics, we now go for transformer mathematics. This is where we begin to talk about large language models. So examples of large language models. So we know transformers power modern large language models. Transformers power them basically. Examples include GPT, Claude, Gemini, and Llama. And the core innovation is attention. And we talked about attention a lot. I think we're still going to talk about it here, or even in subsequent videos. I think there's going to be a video that is just dedicated to the idea of attention. And it's all about computing to make sure for you to know what exactly you pay attention to more than every other thing. So, and then after talking about this now, we have embeddings now. Words are converted into vectors because computer machine does not deal with words, it deals with numbers. So you have to find a way of converting the words to numbers. So words are converted into vectors. Say you have cat now, so you now convert cat into a vector 0 0.2, 0 0.8 minus 0 0.1, and so on. Now embeddings allow mathematical operations on language. So it is embeddings that helps us to do mathematical operations on words, on language, right? So, and then we have the attention mechanism, which you had seen before. Transformer attention is defined as attention of attention as a function of QKV is equal to softmax. Of course, this converts things to probability. Softmax QK transpose over square root of D sub K, all that multiplied by V, where Q is the query, K is the key, and V is the value, like that. So attention determines which tokens are important, basically. So it determines which token should come next. Basically the idea of generative AI, right? So once you write something and the answer is being spewed out, like like that. So attention determines which tokens should come afterwards based on whatever the system has been trained on. Now, softmax converts scores into probabilities. Formula for softmax is like x sub I, which is summation of all x sub I, all over summation across j of e raised power xj. Example, now you have scores 210, and you have the exponentials e raised power 2, that's 7.389, e raised power 1, that's 2.718, e raised power 0, that is 1. So that's exi here, each of them. So it's like E2, E1, E0. And then the sum of all of this now, which represent what you have under here. That's if you add up all of this, you have 11.107. So you can then compute probability for each of the scores. So for the first one, now you have 7.389 all over this, you get 0.665. For 2.718 divided by this, you get 0.245. And this one, now you have 0.090. And then if you add it up at any point in time, you should get 1.0. So it forms a kind of probability distribution. So having looked at the mathematics of the transformer mathematics, then we move on to talk about information theory, where I talked about the Shannon index the Shannon number the other time. Yeah, I think it can be called Shannon index too. So information theory is the mathematical foundation of modern language models. And then we have the idea of entropy. And entropy measures uncertainty. And I think there's an idea of entropy in physics and chemistry, where you talk about the entropy of a system of a maybe if a gas or something. It measures its degree of disorderliness. So in the case of information theory, it measures uncertainty. So and you have a formula, h of x equals minus summation p of x log p of x. Example, if you have a fair coin, probability of getting a head is 0.5, probability of getting a tail is 0.5. The entropy then will be, sum of all of this up. You have 0.5, 0.5, which is 1. So here, this gives you maximum uncertainty, or more like maximum certainty, in fact. So, and then we have KL divergence, which measures difference between probability distributions. So for the formula now, you have d sub kl of p double slash q equals summation of px log px over qx. And you have applications of KL divergence in large language model training, reinforcement learning, variational autoencoders, and knowledge distillation, like that. So our final mental model, modern AI can be viewed as linear algebra, calculus, probability, statistics, optimization, and programming, all leading to artificial intelligence. So if you master these topics and you understand the mathematics behind machine learning, so master these topics and you will understand the mathematics behind machine learning, deep learning transformers, and large language models. So, in case you need to get yourself grounded on all these concepts, just check on this channel, go to playlist, and you see all the playlists of everything: linear algebra, probability, statistics, optimization, calculus, and all of that. So for algebra, so we come to the practice problem. Solve all problems without using a calculator unless necessary. Of course, this is simple. Y is 4x minus 7. Find y when x is n. So just x is 9 rather. That's 4 times 9, 36 minus 7, which is 29. Yeah, 36 minus 7, yeah, 29, like that. So let me just flash the questions and get going. So this is question one right there for you. Question one and two showing. Then you have questions three and four. We can take that much down. Questions three and four. Then question five. We can see questions five and six here. Of course, as usual, I solve two of them. So I'm going to solve problems 8 and 20. So I'll show you 8 and 20 when we get there. So 6, you have 7 and 8. So we are dealing with just multiplication of that simple one. That's easy. Then we have for calculus now the derivative 9 and 10. Then 11. We still 11 and 12. We still have calculus. Find f of x is x cubed. Compute f prime of 2. Then find the gradient. Of course, we know how to do that. So you have partial f, partial x, partial f, partial y. That will simply be 6x 4y. Then for probability now, you have questions 13 and 14. Okay, then you have 15 and 16 showing here. Still, you have probability and statistics now. Then 17 and 18, find the median, which data set has greater variance. That's down statistics. Then 19 and okay, we can show 19. Machine learning and optimization. A regression model predicts y prime equals y cap equals 22. Actual value is y equals 27. Using loss squared error loss, compute the loss, right? And then we have question 20, which we are going to deal with. Suppose the parameter has w to be 12. Learning rate is learning rate eta is 0.05. Gradient is change in L, which is 8. Using gradient descent, that compute the updated parameter value. You're going to solve that. And then you have some challenge problems. Compute the softmax probabilities of 1, 2, 3. We've done that before. So you just need to take exponents of each one, e raised power 1, e raised power 2, e raised power 3. Then get the values, add them together, and then now divide each e raised power 1 by the summation, e raised power 2 by the summation, e raised power 3 by the summation, and that will be your soft max, like that. Then challenge 2, a neuron has x equals 1 4, w is 0 0.2, 0 0.5, then b is 0 0.3. Compute this. I mean, just that'll be 1 times 0 0.2, 4 times 0 0.5. That's 1 0 0.2 plus 2. That's 2.2 plus 0 0.3. That's 2.5, like that. And then there's a challenge 3 too. A classifier predicts P to be 0.95 for the true class. Compute the cross entropy loss. L is minus log P, round to 4 decimal places. So let's deal with the two problems we need to solve here before we get done with this. So let's see that. So problem 8. Problem 8. So we need to multiply 2103 and 42. Easy peasy. You have 2103 and then you have 42 here. So this is a 2 by 2 matrix multiplied by a 2 by 1 matrix. So you have a 2 by 2 multiplied by a 2 by 1. Usually to give you, so cross this out, you're going to get a 2 by 1 matrix as your result at the end of the day. So that helps us to know where we are going. So in this case now, because you have two rows here, so you write 4 2 twice. So you have 4 2 4 2. Okay, and then this 2 1, bring it over here. This 0 3, bring it over here. and then you just go 4 times 2 is 8, 2 times 1 is 2, then 4 times 0 is 0, 2 times 3 is 6. So 8 plus 2 is 10, then you have 6 like this. And that is the easy answer there. So why does this matter though? So why does this matter? So why this matters? Why do we have to do this? So why this matters? Every every neural every neural network, every neural network layer performs matrix performs matrix vector. This is a matrix vector now because it's a 2 by 2 matrix and a column vector. So that's a matrix vector operation. So performs matrix vector or matrix matrix multiplication. Generally in the form z equals wx plus b. Then uh, we also know that large language models, which that's LLM, perform billions, perform billions of this of these operations during training and inference, during training and inference. Yeah, so that's question 8, right? Problem 8. Then we go for problem 20, which involves problem 20, which involves gradient descent. That's about the most important algorithm as far as AI is concerned. So here, suppose W is 12, eta is 0.05, being the learning rate, and of course, the gradient L is equal to 8, you know. So use gradient descent. So that means that W, the new W, or how I like to write it, you can say Wn plus 1 is equal to Wn minus eta delta L. Yeah, grad L, if you like. So we have that. So step one now, step one, step one, we have we substitute values, right? Substitute values. So for these values now, we have Wn plus 1 equals Wn minus grad, eta grad L. So that means that the original W we had, right? That's, you can call that W naught equals 12. And of course, eta is always that 0.5. And then you have grad L, which is 8. So now that means that W1 is equal to W naught minus eta grad L. So W1 is equal to W naught, that's 12 minus 0.05 multiplied by 8. So that means that W1 is equal to 12 minus 0.4, I believe. Yeah, that's 0.4. So I think I do. So step 2 now, we are computing the learning rate times gradient. Okay, there's no point following these steps so we don't get bogged down. So W1 now is 12 minus 0.4, which is 11.6. 11.6. That's the new value of the parameter. And then we keep going, right? So we can keep going and going. Now the question is, why does this matter? We've seen a bit, we've seen why it matters before, right? So we have 11.6 in this case as our final answer, just one step, but we can keep going if we need to do more steps. Why this matters then? Why this matters? Why this matters is that gradient descent, gradient descent is the core, gradient descent is the core learning mechanism. It is the core learning mechanism of modern AI, of modern AI. Every step, every step, rather, every training step follows one, the following. It follows this. It make predictions, then compute loss, make predictions, compute loss, then gradients, compute gradients, then update parameters, then uh then we have the update rule. Update rule, the update rule is something like this. The update rule is this. We have W new equals W minus eta grad L. Okay, is applied millions, millions or billions, millions or billions of times when when training when training neural networks, neural networks and LLMs. Okay, that's why that's important. So on that note, we are done with this. Let me just go through the questions again, and then that will be all. So let's start from the beginning. Questions. Okay. So we have questions 1 and 2, questions 1 and 2, then questions 3, 4. Okay, we can see 3, 4 very well now. 3, 4, then 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. We have 19 here, and then we have 20. Then apart from 20, we have some bonus. We have some challenge problems. Like you have challenge 1. Okay, challenge 1 is showing here. That's softmax probabilities. We have challenge 2 and then challenge 3. So let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, why not go ahead and do that right away? And hit the notification bell so you can always get alerted each time a new video is released. You can also become a member of the channel by clicking on join. When you do that, you see some special privileges that you will have as a member of the channel. Ultimately, don't forget to comment, like, share, so that more people can have access to the great content I have going on. Until I come your way again, keep doing maths right. Bye.